Good morning. Can everybody hear me? Nice that many people came again today, and I will try to write a little bit bigger. Let me recall what we have achieved. We generate random vectors by means of a linear operator n, R, and some Gaussian random variables. This would be an orthonormalized basis of your Hilbert space. The C's are composed of real and imaginary, yet identically distributed random variables of zero mean and 1/2 variance. And R, that is an orthonormal basis. I don't write it down again. These are Gaussian complex variables, and R would be the square root of some density operator, which you can for the moment choose as you like, for some where ρ is some density operator. So it is self-adjoint as a spectral decomposition of some form. Are the eigenvalues and eigenvectors of ρ, which always exist. And I can focus on the case that all eigenvalues are positive. The zero directions will not contribute here to the random vector. I can omit them immediately and only keep the positive ones. And it is a density operator with trace unity. That means, just to repeat what the square root means, I should here put that. I put also the numbers. That would be number 6. And that means this symbol here means the following. The sums always go from 1 to capital N. The square root of the eigenvalues, the original ρ, and the same basis. That was 29. And it also means that the inverse of ρ exists, and you can write it down with the inverse eigenvalues, like this. This exists. So, and now, those vectors are in general not normalized from the beginning. Their normalized counterparts are the psi's. So I normalize this phi to unity, and these are the random vectors psi of unit norm. And then that was 24. And now you can consider each such normalized random vector as the initial condition of a dynamics. So this would be the initial condition without an index. That means the starting point of the dynamics. And then you have some propagator of your dynamics of your choice. And this generates you the state at time t. This can be generated by a time-independent or by a time-dependent Hamiltonian. And I should emphasize that it does not matter what kind of Hamiltonian. It can be integrable, non-integrable, whatever. It's just the dynamics which this Hamiltonian generates. That was essentially number 19, rewritten a little bit. And then also you can, with the same dynamics, propagate your ρ, which you have chosen. But first get the beta, that is so to say the initial condition of your propagation. That would be 25. And then everything is now set up. That's the setup. Whatever I did not say is not required. All requirements are here. And then the main requirement follows immediately. then the expectation value of some observable O at the state at time t is very close to the expectation value in the mixed state rho of the same observable for most dies, which are generated in this way, plus 26. And provided, here is the main condition, provided that the trace of your rho, which you have chosen, the trace of rho square, the purity is small. And this is, that was number 9. This is equivalent to requiring that the maximal eigenvalue of rho small. These are the main requirements for this statement. Besides, apart from this, there is no requirement. I had very good feedback yesterday, today, so I should maybe add, in the quantitative version of this statement, there was the operator norm of the observable appearing. And you can say some observables have infinite norm or arbitrary large norm if the space is sufficiently large. Then this estimate is useless. But that is not entirely true. O is not some Hermitian, some crazy arbitrary Hermitian operator. It should model a measurement device. And the measurement device has only a finite range of possible measurement outcomes. However large your Hilbert space is, this is limited, this measurement outcome range. Therefore, the operator norm is limited by this range. And you have a certain resolution limit of your measurement device, and the measurement range divided by the measurement resolution has some finite value, maybe 10 to the 10. Your measurement cannot give you more than 10 in significant digits, for instance. And then this ratio of measurement range and resolution is the essential quantity, and this will be limited. And this should be always kept in mind in this inequality. But these are the two main things which should be satisfied. The deviations, if the deviations are smaller than the measurement resolution, then you cannot tell the difference. And for sufficiently small purities, that will be the case for practically all initial conditions. That is the spirit. But this is all, I should also mention, this is true for any given t. And it is, or you can also throw it is true for the majority of all times in a given time interval. But it cannot be true for all times in any given time interval. That cannot be true. You always have these revival properties, and you have very rare excursion from what you usually expect. This can do some strange things at very rare times. These are exactly those exceptions here, where you go far away from the typical behavior. So, yeah, that's it, what I wanted to say. So you can practically imitate, if you give me a starting density operator, whatever you like, and then I construct my R, I draw random vectors, and these random vectors imitate your Sorbel. And if you draw another one, it behaves almost the same. That's the method so far. And as I say, rho is so far at your disposition. So now you can choose interesting rows. For instance, that was this was the summary of yesterday. Now I continue. Equilibrium. Initial condition. Write bigger. No. Equilibrium initial conditions. So let us focus. In general, this can be a time-dependent Hamiltonian generating the dynamics. Now, in this chapter, we focus on time-independent Hamiltonians of the special form and rho of the special form of the form rho is some function of h, whatever it is, rho square psi, some positive function, of course, exponential of h or whatever, some function of h such that rho satisfies what it has to satisfy. Then it follows, I don't have to prove this, such a rho commutes with h. It's easy to see. That means rho is a constant of motion, does not change in the course of time. So rho of t will be equal to the initial rho at any time. It's a constant of motion. And this means if the rho in addition has a small purity, if this happens to be the case, then this means that if you draw random vectors according to this recipe here, then all these random vectors will always stay very close to a time-independent value. That's the statement in a time-independent rho for a steady state. As usual, so the rho is so to say, you can call this an equilibrium, a density operator. It does not change in time. You could call this equilibrium. It is steady. Rho is a steady state. And but of course, the corresponding psi's are not steady state. They change in time. That is the same. If you are in an equilibrium situation, the pure states still change in time. Just the density, the statistical operator does not change in time. That's the usual situation. So what? No, the density matrix is any function of h. Yeah, if you have, yeah, an example follows immediately. But you can immediately conclude, if you choose rho in this way, then this rho commutes with h. No, I can't take any function of h. Sorry?
That this is not the only case that.
No, I do not.
Rho can change with time, and
Yeah, in general, it can change.
He's talking about a very special case where Hamilton rho is chosen. That
Time independent. Independent. Yeah. In general, rho changes in time, but for a rho of this form, it will not change in time, because rho commutes with h, and then this means the time derivative of rho is 0. It's given by the commutator. No, I call it equilibrium.
not a thermal equilibrium. It's not thermal equilibrium.
No, it is not thermal equilibrium. It's a steady state, if you wish.
Infinity, we should
Equilibrium means time independent, steady, and thermal means the steady state agrees with one of the canonical ensembles from textbook statistical physics. I give you now examples. You have still many possibilities. So example 1. I choose, so let us assume H is an energy shell. For the sake of the example, let us assume I focus on an energy shell spanned by all eigenvectors whose eigenvalues are in a small energy interval, and choose f of x, and the dimension is n of this Hilbert space. I choose f of x is 1 divided by n, which is also a function, just a constant. Then you get rho equals the so-called microcanonical ensemble, which is 1 divided by n times the unit matrix, or times the identity. For this choice of f, you get the microcanonical rho. So I don't write it down. That is the microcanonical ensemble in this example. And the R operator would be the square root of rho, which in this case is 1 divided by square root n times the identity. This example. As usual, as I always assumed, I assume again the dimensionality of this energy shell is large, and therefore you see immediately P max, I mean all the eigenvalues are 1 divided by n. It's then indeed small, condition is fulfilled, and I can conclude that for any observable and any initial state which is fabricated according to this recipe, with this specific rho, will give you, most of them give for most times the microcanonical expectation value of this observable. If you choose rho or R in this specific way. For any given observable and any given arbitrary but fixed time point t. This is true for most psi's. So if you can now focus, forget the time evolution, focusing on time 0. I just choose the time equals 0, then I have the initial vector without the time argument. This is essentially what they call canonical typicality, or the non-dynamical typicality. This finding corresponds to, I call this non-dynamical typicality, or just for the sake of the name, canonical. I call it canonical. I mean, it's not really their canonical typicality. Which I cited at the beginning. See the beginning. This was put forward in the paper by Goldstein, Lebowitz, Tumulka, and Zangi, which I cited, and by Popescu, Short, and Winter. This observation, they had a specific setup that the system consists of a little subsystem of actual interest and a bath, and then their statement concerned only the subsystem, which is a special case of this one. And then you can, of course, integrate out the bath, and there appears, after integrating out the bath, appears something like the canonical density, and then you call this canonical typicality regarding the subsystem, but the general spirit is exactly the same. This is the concept of canonical typicality or non-dynamical typicality. They claimed, or their viewpoint was, this surprising property practically, I mean, if this is this is essentially the identity, then essentially each vector is equally likely. Each normalized vector on the unit sphere is drawn with equal probability, and if you draw one of them, you get the microcanonical expectation value for your observable with extremely high probability. In their system, in their subsystem and bars set up, they said this is due to entanglement between subsystem and bars. But I believe this is not really the crucial point. This is just a property of high-dimensional spaces. Has nothing really to do with entanglement. That's, yes? This itself, you mean?
If in the high dimension, if I'm randomly picking
Yes.
the state, so the most probable state is the maximally entangled state.
Yes.
So then entanglement is also playing a major role in deriving this result when you're claiming in the in the higher dimension. Am I right?
Kind of matter of taste.
Right.
If you like it or not, entanglement always comes.
Yeah, but
Peter is saying.
The way you just explained the Popescu et al. Result now, it seems that they dealt with small subsystems. So in their language, this O would be a local operator. But is this an arbitrary operator the way you are?
This is any operator of bounded norm. But this covers the situation where you have a bus and a subsystem. Then the operator only acts on the subsystem, and if you like, you could integrate out the bus part. No, it's not necessary. So this is the first example. You recover dynamical typicality. So in short, the vast majority of randomly sampled normalized states looks practically indistinguishable from the microcanonical ensemble. It imitates this ensemble. And this also means, Marcos is still not here, I think. In our last nice conference in Kyoto, he raised the important observation that it is very difficult to find non-equilibrium states. That is his problem as a numerical person. Finding non-equilibrium states is not very easy. And that's the reason. Almost all states look like equilibrium states. It is quite hard to find a state which notably deviates from the equilibrium behavior. That's also here observable why this is so hard. They are in some sense exceptions. The non-equilibrium states psi. Of course they exist. These are just those which do not satisfy the equation very well. They exist. They are not very many among all of them. So, this is the right thing. I will now immediately, later we will see a way out, how to generate non-equilibrium states according to this recipe. I also could say, here the observable is fixed, and in your mind you could sample all normalized vectors on the unit sphere with equal probability. Then the statement is most of them look like equilibrium. But it is equivalent. You could fix one vector psi, and now you let rotate the basis of O. You start letting rotate the eigenbasis of O with Dhar distributed unitary transformations. The eigenvalues are kept fixed, but the basis starts rotating, and all orientations of this eigenbasis appear with equal probability. That's equivalent. So you have a fixed vector psi, And now you sample over all observables with the same spectrum, but with randomly sampled eigenvectors. And then most of these observables look like equilibrium, produce the equilibrium value. That means that was also rediscovered in the literature many times. If you have any state, it can be equilibrium or far from equilibrium. Most observables will not notice this fact that you are out of equilibrium. Most observables still look like equilibrium. That's just another side of the medal, which was also discovered and rediscovered many times. Okay, example 2. Now I choose H is the full space, so to say, the original high-dimensional full space where your model lives from the beginning. And I choose f equals some constants, which I call e to the minus 1 times e to the minus beta x. That is also a function of x. And then you obtain rho will be the canonical rho, which is c to the minus 1 e to the minus beta h. That's the canonical ensemble. I choose my f like this, and the c is the partition sum trace over e to the minus beta h. For this choice, you get the canonical ensemble, and the corresponding air operator would be the square root of this is e to the minus 1/2 e to the minus beta h divided by 2. If you use this operator here to generate your vectors, you get vectors which imitate the canonical ensemble. And I have to verify my condition, P max must be small. So the maximum, I mean the eigenvalues are obviously e to the minus beta en. The maximum would be this one, so the minus beta en. En would be the eigenvalues of the Hamiltonian H. Then this would be the trace. This is the partition sum here, the trace evaluated in the energy eigenbasis. And that would be the maximum of all of them. The maximum, sorry, that is the minimum here. E to the minus E minimum. That is the largest possible value which P can have. These are the eigenvalues of rho. And this you can rewrite as 1 divided by sum over e to the minus, not beta, I want En minus E min divided by kBt. Beta is 1 divided by kBt, and I take this downstairs, En minus E min. So if you have many energies which deviate from the ground state energy by less than kBt, then this is a big sum. The sum takes a big value. If many energies are relatively close to the ground state on the scale of the thermal energy kBt, then this will be a large number. This will be small. Yes, and that is very common. That, I mean, the spectrum is really very dense. If you don't happen to have a gap for a non-gapped system, you have many energies within a distance of kBt from the ground state, and then it will be satisfied. So under many usual conditions, this works. In other conditions, you could fix the problem, but I don't go into the details. So in most usual examples, it is small enough. That means in the canonical ensemble, you can get canonical expectation values by sampling pure states according to this recipe in very good approximation with very high probability. Okay. I recall that any basis is fine. This construction is invariant on the basis transformations. This could be, for instance, the product basis of the non-interacting single particles. Could use and then sample random vectors like this. So now a little modification. Instead, of 38, I take a modified R operator. Namely, I simply take R equals e to the minus beta h divided by 2. I simply omit this prefactor. It's just a constant. It is a change by a constant. I take this R, because now it is not anymore the square root of a density operator, but that's not matter. It's a very trivial modification. This simply means every vector phi acquires an extra factor square root of c. That is the consequence. Each phi acquires an extra factor square root of c. So every phi in the original construction picks up an extra factor e to the 1/2. It's a trivial modification. It does not change anything. As soon as you arrive here, this will all be fixed by normalization. It does not change, except that phi picks up the factor c, and instead, or did I forget it to write it down? Oh, that was a mistake. I should have said this. We have proven that in this construction, every phi has a norm which is very close to unity. I forgot to say this. This was another result of yesterday. The norm of every phi is with very high probability close to unity. And now it picks up a factor square root of c. Then the norm of phi, of this very normalized phi, will be very close to c for most. It's just a renormalization of phi. This is almost trivial. That means by sampling a random phi with this even simpler R operator, you can generate, with very high probability, you generate a partition function, and this gives you the whole thermodynamics. Yeah, rho is now not 1. I mean,
Just R.
Only R is. It is not rho, but it is a trivial factor. Everything. Okay, let's put it this way. I put here an extra factor c square root of c. I only need these two things.
You should only look at equation 1 and the new R.
This one.
You should ignore all the rest.
The rest is
What do you have?
For the rest, the old thing is true. It does not change because here everything drops out. But if you look at these two things, with the new R, without, it's just a constant. It differs by a constant. And most of these phis which you now generate, instead of having norm close to 1, they have norm close to c. And after you have calculated the c, you quickly divided by square root of C, and then you continue. And then you have both things. You have expectation values of operators in the canonical ensemble, and you have the whole thermodynamics as well in one step by drawing one random vector. So this gives you also the thermodynamics.
I suppose you still have to do like a couple of just because you still derivative.
Yes, that's true. That's true. Yes. Just in principle, you are almost there. You are right. Note, this is relatively easy. I mean, applying such an R, first you generate here a random vector, then you have to apply this operator R. But this is not so difficult actually in numerics. That is just imaginary time propagation. That's just, if there would be an imaginary part, this would be a propagator. This is like an imaginary time propagation, which is numerically not so difficult, actually, especially for small betas for large temperature. This is relatively straightforward to really execute. Essentially, this is the content of the papers by Sugiura and Shimizu in the Physical Review Letter 11, 01, 04, 01, 2013. This is essentially, I mean, as I said, it's all in my language and in my notation, but that is the main idea in this paper. You get the expectation values and the thermodynamics, and the microcanonical version, where you get the microcanonical expectation values, and they also show how to generate the microcanonical partition function and the thermodynamics along the microcanonical formalism. Same thing is in their paper, the same authors in their paper, volume 108, 24, 04, 02, 2012. It's a pair of papers on the canonical and the microcanonical version of these ideas. And there they coin the notion that such random states are so-called thermal pure quantum states. They now really imitate thermal equilibrium densities. In this case, equilibrium is thermal equilibrium.
Peter, can I add that this first also Sugiura is participating? I don't see him now, but anyway, I can ask him directly a question.
Did you see him before? Yeah. Ah. Then I forgot who is who. Yeah. But if you go into the literature, you find precursors. Harms and Hans de Rardt. They have many papers which in similar spirit, but the closest is probably this one, Physical Review E, 62, 4365, in the year 2000, and many others. It's just one. There are many precursors. So apparently in the numerical community, in several other communities, very closely related things have been discovered independently and sometimes earlier. For instance, Peter is even better. It also works at low temperature. This is not any more satisfied. Emax is not any more small. His algorithm still works there. And in theoretical chemistry, I have seen that they also independently rediscovered such things. And in informatics and mathematics in general, under the keyword trace estimators, there are very similar concepts around. So that was about non-equilibrium cases, about equilibrium situations. Now I am, of course, mostly interested in non-equilibrium. Initial So for time dependent Hamiltonians already, now you could generate your rho simply from the initial Hamiltonian. May be interesting. For instance, you could start in the canonical equilibrium, which corresponds to the initial Hamiltonian, but then the Hamiltonian changes. I think, I have a feeling that this already could be of interest, but I did not work it out, and I did not really find an interesting specific case, but maybe you have an idea how to. I find it remarkable that this whole business works for time-dependent Hamiltonians. But unfortunately, I have no very striking example at hand. But
I just take some initial Hamiltonian, right, and I just start with it, just quench it to a final one. Already, this should tell you how it relaxes to the final thermal equilibrium. That's possibly the simplest thing to study.
No, unfortunately, it does not tell you how it does do it. It simply tells you it relaxes the same way as this rho. Or it tells you almost every psi relaxes the same way. But it does not tell you how it relaxes. That cannot be deduced from here. It just tells you they behave the same way, but not how they behave. That is an intrinsic limitation of this thing. So, but now, from now on, now I focus on time independent. Time independent. From now on, I focus on time independent Hamiltonians. The usual situation, typical in a usual experiment, situation, or also in an experiment in your mind, you have several things. The system has a well-defined energy. You know the energy with some energy uncertainty. The energy is more or less known. Maybe you don't know its value, but you know it has a specific macroscopic value. Therefore, you should work in an energy shell, or use an energy shell as your Hilbert space. You know the system lives in a relatively small energy interval. It is confined to a reasonably well-defined energy interval. So you would work with an energy shell. And second, the system is initially out of equilibrium. out of thermal equilibrium, I mean. That means there are at least some observables whose expectation value is different from the thermal equilibrium expectation value. That means expectation value of some observables, AK, I call them AK, K goes from 1 until you have certain observables, AK, K of them, they assume they take certain non-equilibrium values. The expectation values of those observables at the initial state take some values, I call them alpha K, which are away from the equilibrium values. That is a usual experimental situation out of equilibrium, I think. So now it is, of course, very natural to include those additional constraints into your rho, so that trace rho AK is required to be alpha K for all those extra knowledge which you have. I select a rho operator which automatically has these expectation values. And now, if I construct my random vectors according to this rho, I know almost each psi vector will have this expectation value. So I generate now random psis which have these non-equilibrium expectation values at the beginning. That's a trick. And I mean, the assumption is, of course, you should not have too many Ks, otherwise. As I said, this can only be satisfied simultaneously for a limited number of observables at the same time. So the assumption is K is still very much smaller than N, which seems reasonable to characterize an experimental non-equilibrium situation, a reasonably small number of out of equilibrium characteristics should do. For instance, even if these are densities and you have to specify the density at many places in the space, it will still be sufficient to specify it at K places which are still very much smaller than N. N is of the order exponential of the number of degrees of freedom. So you have 10 to the 23 particles. N is 10 to the 10 to the 23. So you can specify your out of equilibrium density at many places in space. According to their values, it is still fine. So I think it is reasonable to say that you can specify any realistic non-equilibrium initial condition like this. Apart from that, the initial state is largely unknown. You know a certain number of non-equilibrium features of your initial state, but you don't know all the details of your initial state, of course. Apart from some knowledge, it is largely unknown. So, if you repeat the same experiment in the same lab, you will practically certainly pick another initial state. It will have a similar value of those observables, but otherwise it will be very different. You cannot reproduce the microscopic initial state in a second experiment exactly. And more so, if somebody else repeats the experiment in his other lab somewhere else, it will be a very different vector. So you cannot repeat in an experiment the same initial state psi apart from these approximate given initial values here. So the question arises.
He's going to explain.
This is the psi, yes? Sorry?
You're going to explain how you construct this.
Yes. This psi is the psi which you generate by such a rho which satisfies these conditions. Oh, it is the same psi. Yes. I choose a rho which satisfies the extra condition. Then R is the square root of this rho. And then I sample random phi's with this R. And then I normalize them. Yes? Yes, it is random. That's true.
So rho determines R. R is not random.
Yeah, this is not so important here. That is more discussion. I generate an initial state in the experiment which satisfies approximately the known conditions. And if I realize it again, I will get another. You are right. This is now just an initial state of a given experiment. So let's tell me only in words what I mean. You generate an experiment in an initial state which satisfies what you know about the experiment. But then you repeat the experiment, you get another initial state in your experiment, which usually... Oh, let's say they have nothing to do with this psi. I make the connection immediately. You make another experiment, you repeat the same experiment, but you get another initial state in reality. You cannot reproduce it.
But I think this discussion is confusing. Probably I won't agree with you. For example, but anyway, mathematically, you first choose rho deterministically, such that satisfies this. But this choice is, of course, not unique.
Yeah,
Existence is not guaranteed.
I come back to this.
But you choose this.
Now let us close. Everything disappears from the blackboard, and I tell you, if I repeat an experiment, you cannot reproduce the initial state.
That does not justify the use.
No, this blackboard is not visible now. And now you can wonder, for instance, a gas in a box with a hole, you repeat the experiment, it is in a different state. Why does it give you the same result? Why is an experiment reproducible? It is not in the same initial state. You cannot control it. You have chaos. They evolve in a completely different way. Why can you reproduce an experiment at all? Because you cannot reproduce the initial state, and it generates chaos. And this, now I open again the blackboard. This approach can explain this question. You generate random vectors where you only know this little information, and for the rest, you don't know the details of psi. But if you generate them according to this, you get exactly what you see in the experiment.
But I don't agree with you. I'm not saying that you are choosing
Yes.
specific measure. You are choosing some specific. That choice is very hard to justify. I agree with you.
I will come back to this. What is the right choice of the many rows which satisfy this equation?
The choice of random measure, generating random vector.
Yes.
But anyway,
Okay.
keep it in the black part.
That was just physical discussion. Now let's come back to the mathematics, if you wish. The remaining task find a row which satisfying 6. It must be trace 1, it must have small purity, and it must satisfy all these extra conditions. That is what rho has to satisfy. Now, I assume, as assumption, at least one such rho exists. That is the assumption. Otherwise, I would call this an ill-posed situation. If you have given conditions which cannot be satisfied by any rho, not even one pure state exists which satisfies all your experimental conditions, that would not be. Then something is thick. This is a thick situation. I assume there is at least one rho. But if there is one rho, you see these are k linear equations, and there is another one, k plus 1, and the next condition. You have about k linear equations, but if you write this in a matrix form, you have about n square numbers in this row. The row has n square entries, independent real numbers there. So there are, of course, many solutions of these equations. It's not at all unique. If there exists one, then there exists probably many. So, problem, then it is quite clear that there are many solutions exist. If there is one, there will be many, which satisfies all conditions. And the problem is, if you have two such solutions which satisfy all the conditions, then there exist observables such that all of them generate the typical dynamics. If you sample random vectors, all of them which you sample in this way reproduce this one, and those which you sample in this way reproduce this one. But they, in general, generate different dynamics. It's usually not equal or differs from other one. Both now generate a random vector ensemble, which this ensemble imitates this behavior, and this ensemble imitates this behavior. But because they are different, for instance, at time 0, they are these exact rows. If you choose the right B, they will produce different values. So what is now the right one? Both of them satisfy all conditions. For example, you could choose both these rows satisfy this condition, but now secretly I have an extra condition secretly, and this one satisfies the k plus 1 condition with some a alpha k plus 1, and this satisfies the condition with a different alpha k plus 1. I just don't tell you that I constructed in this way. And then for this observable ak plus 1, they will have different values at time 0, for instance. So the question is, what is now the right row to choose? So which is the right? What is? There are many possible rows. Which is the right one? You need an extra condition, obviously. So my extra condition is the following, the unbiasedness assumption. This is my extra condition, which will then select one unique row. The abbreviation is unbiasedness assumption. So I write it down. If two random vectors psi1 and psi2 satisfy psi1 of this special observable AK, psi1, if they have exactly the same expectation values for these observables AK, so exactly equal. An exact identity, not just an approximation. If they are exactly equal for all K, these two random vectors produce exactly identical expectation values for all these observables, then they are realized in the random sampling procedure with exactly equal probability. That is the condition. If they have exactly equal expectation values, they are exactly equally likely. That's the extra condition. Note in general.
I understand, but that cannot be a mathematical. Probability is of getting a thing.
Yeah, but you,
I understand
you
what you
just pick two which happen to be.
It is. They are very.
Yeah.
So you are.
There exist, certainly there exist vectors which are, and you can group them into classes.
So this is a problem of finding row satisfies this condition 42 and have maximum entropy.
Yeah.
I guess the one solution you have to slightly modify, but one solution is given by Jonathan Oppen. They treated sort of grand canonical type ensemble for mutually non-commuting.
Well, I will give you a very strong argument why this is the right choice later.
Yeah, but I think the ensemble constructed by Jonathan and others, I believe that satisfies this.
Okay. And it will be the same result in the end.
They only constructed the ensemble. And make use of their ensemble.
You can tell me later. I don't know exactly what you're talking about.
These capital AKs are some kind of densities. Probably one can think.
Yeah, you will see the resulting row has not the form of a generalized Gibbs ensemble. That will not satisfy this condition. So you note in general, the psi's anyway they generate approximately equal expectation values always. Most of them produce approximately equal expectation values, but here I require that they are exactly equal, not just approximately. I think this is a natural assumption. You have these non-equilibrium constraints, and for the rest, your state is largely unknown. So you simply say if they have the same expectation value, they are equally probable. That is a natural assumption. All available information is here, and for the rest, you have no information. So you assume something like this. Sorry? Now that is the initial, before you evolve it in time, without the time argument. just a randomly sampled vector, which later serves as initial condition. So later will be a strong argument if I have still time. So I think this is a relatively natural extra assumption to select one row finally. So now I work with this determination of row according to this requirement. Given any row, I consider a row and its eigenvectors are called Pn and its eigenvalues are Pn, its eigenvectors are Pn, are n, and you can write the whole recipe as, you have to speed up a little bit. So the y's are just, you plug everything in. You construct it according to this recipe. That is the spectral decomposition of rho here. That is and then you take the square root, which looks like this. You apply it to this. Here you choose the basis of rho. You apply this, and then you normalize it. Then you can rewrite all these steps in one line like this. It's just rewriting this construction, including the normalization. And then no, this is the same row for all. I need a row which satisfies all conditions simultaneously. Same row. Yeah, if you sample random vectors normalized, and if you take two of them which have the same values, then their probability must be equal. The probability density at this point, then you are fine. Yeah, whenever you have two of them which have equal exponentially, they must be equally likely. Yeah, the same for both. For all cases, exactly equal.
Are you giving a construction of this row explicitly?
Mm-hmm.
And then we can discuss.
Probably it's not possible really to do it. The probability, I call the probability, I must now define a probability of these random vectors. And I identify this with the probability that these y's are generated by definition. Probability to draw this vector psi is given by the probability that these y's appear. That is practically definition. I don't know how to give a probability in Hilbert space otherwise. The probability of psi is the probability that these random vectors are realized. So it's just all these random vectors, y1 to yn. And now you can write, it's just that is just a transformation of variables, if you wish, from the random variables c to the random variables y. That is a transformation of variables. So v of y you can calculate as usual. This is the integral over all real and imaginary parts of all the cn's. Over all an's and bn's. This would be the probability distributions of the C's. I write it down immediately. And this is the delta function, which picks those y's. So it's very confusing, I know. This is the distribution of the C's. They are all Gaussian distributed. This is the normalization with mean value 0 and variance 1/2. So I could write it like this. This is the distribution of the C's. Each Cn consists of An and Ibn, and all of them are Gaussian with 1/2 variance. You can convince yourself that's the probability distribution of the C's. And this is this function, the function which connects the C's with the Y's. That is exactly this function here. This I would write now as the function y of C. Y. For each vector C, you get a y of C according to this recipe. This n-dimensional connection between the old variables and the new variables is here. And this y is the argument of this distribution. That is the usual formula how to transform an original probability distribution for the original variables to the new transformed variables. That is probability theory. So that is what you have to do. Now I omit. I mean, you can plug this in. Of course, you have to go to An and Bn variables, two real integration variables. You calculate and calculate. And finally, after you have calculated a lot, get the result. This is some constant times. Of course, you find that these vectors must be normalized. Here you find O to the -1 psi to the power n. That's the end of your calculation, and that is a normalization constant. n-1 factorial 2 pi to the n. Here you have the determinant of your row matrix that you find after carrying out this integral. So that's the new distribution of the y's. And now comes the essential step. Now I focus on such a row which satisfies the unbiasedness assumption. And that means for whenever psi with equal values of A psi k, that is expectation value, must be equally likely. Whenever these values are equal for two psi's, they must be equally likely. That means this probability distribution, or here, the same, it can only depend on these quantities. It can only depend on these quantities. Whenever you know values of these quantities, you get the same value for W tilde. W tilde is constant whenever these values remain fixed. And psi may change, but these values remain fixed. Then this density cannot change because it must be exactly equal whenever all these values are equal. That means this function can actually only depend on these quantities. Now, that is trivial, and this does not depend on psi anyway. That means essentially this piece here, that is the non-trivial part, there must exist some function, I call it h, and this can only depend on these quantities, a psi a. That must be a function of those k quantities. That is a consequence of the unbiasedness assumption. That's the essential step here. Because of this assumption, I can conclude that this w and therefore this denominator must be a function of these k numbers only. Now you can, I give you a heuristic argument. I can expand. I expand this around all a's being 0. I give a Taylor expansion here. I expand. That is the value h when all arguments are 0. And then I take the derivatives at 0, lambda k. And these, now you have the increments. This is the derivative of h with respect to the k's argument, a psi k. And that is, so to say, the deviation from 0. That is, of course, ak. And that would be the derivative here. That is the derivative h by d by the k's argument evaluated at 0. That would be h evaluated at 0. To expand this function around 0. That's the contribution. At 0, these are all the derivatives with respect to all arguments evaluated at 0. This I call lambda k. And these are the a psi k's. I rewrite it this way. Plus higher order terms. And now I make it short. No. This is a Taylor expansion, not a series expansion.
You're not dropping.
This is just the rest term in the Taylor expansion. I just don't write it down, but it's the rest in the Taylor expansion to second order. And now, I have no time to write it down. It is, one expects that this rest term cannot be written, the rest, this is the rest, here rest, cannot be written in the form psi, e psi. The rest cannot be written in this form with some Hermitian operator unless b equals 0. This has not the, for instance, this is bilinear and psi, but the rest will be of higher order expected. Will not be, will be of higher order. These are the quadratic psi's. The rest will not also be quadratic. That is the argument. There will be no Hermitian operator such that you can write the rest in this form. That should be expected. But now, I mean, the whole thing here, because of lack of time, looks like this. This is over all the k's, lambda k, ak, okay, plus the rest. And this is the form of a Hermitian operator, psi and the Hermitian operator, psi and the Hermitian operator. And this cannot have the form of another such structure with a Hermitian operator, unless it happens to be 0. Therefore, it must be 0. This is the argument. I can give you a rigorous proof, which is very long, and you won't learn much. But this is the main argument.
You wanted an exact equality. Then you're throwing off some terms.
Yes.
How do you prove?
Because the rest cannot have this form. There will not exist a Hermitian operator so that this rest has for any psi exactly this form, unless it is exactly 0, then it has this form.
Why does it have to be this? But we're assuming that each term in Taylor expansion.
No, it's just the rest. There is one term, the rest. It's one term, not the series expansion. It's the rest of a Taylor expansion. And this rest cannot have this simple form with some Hermitian operator, except if it's 0. Then that is also a possibility. No, I mean, if you would write the next order, it would be in 4th order in psi, 6th order in psi. It will never again be 2nd order in psi. All this, it is somehow, it is not rigorous. I have a rigorous proof, which is much longer, and you don't learn much. But I think this is the intuitive argument. This is the, yeah. So if you believe this, it can be also proven more rigorously. I mean, unfortunately, they are normalized. Yes, these are just, no, they are defined like this. They are real numbers. For instance, if they were not normalized, but they are, unfortunately, then you could simply multiply each psi with a constant. Right. Then it must be 0. But because they must be normalized, it is more complicated. But if they were not normalized, it is obvious that this must be 0.
The assumption is.
Yeah. But why should this not be, not analytic, twice differentiable? The Taylor expansion exists to 2nd order. So then this would be 0 here, and this is true for any psi. Then you can solve. You find rho equals lambda 0. Lambda k, ak to the -1. Now you have found a unique rho which satisfies the condition. This operator must be equal to rho -1. That would be the solution. So a more rigorous derivation, how much? Here is not very much. Can also be provided. And you see the number, you have now k plus 1 free constants, lambda 0 until lambda capital K. These are unknowns, so to say. You have to fix them. And you have exactly k plus 1 equalities. One condition is trace rho equals 1. And then you have k conditions for the alpha k's. You have exactly k plus 1 linear equation for k plus 1 coefficients lambda. Now, of course, the issue whether a solution does exist is again a very subtle question. But if one solution exists, you will expect it is the only one because it's a set of linear equations. You expect that then the solution is unique. Okay, so unique solution. for k equal 1, I have worked this out. The proof or the considerations when it is unique, and why. And in particular, it follows every solution which is not of this form is necessarily biased. It will violate the unbiasedness assumption. Now, I have no time left, but I can simply tell you, you can call this ensemble, which is constructed according to this rule. This is the ensemble E. And you can define an ensemble S very shortly, which consists of all vectors which satisfy this relation exactly. All psi's which exactly satisfy this condition, not just approximately. In the ensemble E, they only so far, that is the so far ensemble. S is a new ensemble where all these relations are satisfied exactly. This is the ensemble which I considered so far. And S is a new ensemble where all relations are from the beginning satisfied exactly. That is not the case in my ensemble. They are only approximately satisfied. They satisfy strictly all these relations. And then the main theorem almost most vectors from one ensemble behave very similar to most of the other ensemble. This is the main argument. This is the strict ensemble, therefore S, the ensemble which strictly satisfies this. And that is my ensemble, but they behave essentially the same. That means if you are not satisfied with my unbiasedness assumption, at least it imitates such an ensemble very, very well. So I think I can give you the reference for the rest. Cannot finish. This equivalence has been proven by a paper by Jens Eisert, Gross and Müller. No, first of all, Boris Fine, which we'll also talk here. I found out a very similar result. This is the paper by Boris Fine. Then Markus Müller, Gross, Eisert, Communications, Mathematical Physics. There they have proven the equivalence of the two ensembles for k equals 1. They are for k equals 1. Here you can find the details I had to omit here. Physica R. This is in press. This is the special issue dedicated to Chris Vandenbroek. But you can find it on Google very easily. Just type in on Google why are macroscopic experiments reproducible. So under this, if you type this in, it should appear. It is in press, but the proofs are already out. You should be able to find it. Otherwise, I can send it to you. The paper and press. There, the missing details and the missing end of the lecture is there. Thank you very much.
So I have to take back my comment about the similarity of this thing and what Jonathan. A different thing.
That's true. But the main, the upshot of this approach tells you also you have chaos and the single realizations psi look very differently if they start differently. For most observables, you will not be able to tell the difference. That's the main result here. It's not a contradiction. It covers chaos. And it covers the reality. Why are in real experiments you supposedly have chaos? And you do see the same results if you repeat the experiment. Also, you cannot reproduce the initial condition. Fact. And this somehow explains this. Yeah, that's true. But if you do an experiment with a little bit different initial condition, you get the same result. That's why experiments can be reproduced.
I don't agree that this explains this. Fact is, that's a base. I mean, constructed sort of very nice model which covers this, covers the phenomena that topic experiment are reproduced.
But
Not given.
you know these constraints, and for the rest you know nothing. So they are apart from this equally likely. That seems a natural approach.
If supposing I'm looking at an experiment like free expansion of a gas, here of course we know that if we repeat the experiment, you get the same results, right? But there I would say because what we observe are coarse-grained variables, right? This is true even for a classical system, and it's because we are looking at coarse-grained variables. Does that? Is this also something there in this picture?
I'm not convinced if this is coarse-grained. This can be a microscopic observable, measuring the velocity of one atom at one position. This is admitted as an observable.
Isn't that like you do see repeat the experiment, you reduce, and this is true even in classical system. There can be a different understanding of just because we observe our coarse-grained variables. That a possible definition which seems different from this.
Well, maybe if you consider this as an explanation. Okay.
Which is the correct one. And it looks like two different explanations.
Yeah.
Other quick comment. Okay, if not, let's thank Peter again.